I'm Sean Parent. I'm a principal scientist at Adobe Systems. I've been there now just over 20 years. So I've done a lot of things there. Lately I've been working on mobile digital imaging and some web-based digital imaging. It's pretty interesting work. I gave a talk at the Going Native conference 2 years ago now that was entitled C++ Seasoning. How many people have seen the talk either? Wow. Yeah, so lots of people have seen the talk. It's like 100,000 views on the website now, which is pretty stunning. So it was very well received, and a lot of people suggested that I write a book based off that talk. So what I've done is I've started a book, and I outline the chapters, and each time I get invited to go give a talk, I flesh out one of the chapters for the book. So hopefully eventually this book will get written. Right now, we are here. Now, for people who have followed any of my talks, I've done talks after this point, and I've done talks before this point. I haven't given this talk, so why didn't I give the talk in the middle? Well, it's a bridge talk. Kind of ties the start of the book towards the end of the book, and I didn't think there was anything of particular interest to give in this talk. But last February, I got invited to give a talk. I gave a talk on concurrency as a keynote at Meeting CPP in Moscow. And after that, John asked if I would repeat the talk at C++ Now in Aspen. I agreed. And then a couple weeks before, he sent me an email and said, "Sean, we're short on tutorials. Can you give that keynote as a tutorial?" So I obliged, and I did, and it worked out pretty well. I got an award for Best Tutorial and Most Useful Talk. So then John asked, could you give a talk at CppCon? And I said, well, since it worked out for a tutorial, this chapter would make a good tutorial talk. So I proposed this talk, and I get an email from John and said, we're very excited about your talk. We're going to make it a keynote. So thanks, John. So each chapter in this book to be written has a goal. And the goal for this chapter is no incidental data structures. And the word goal here is chosen very specifically. This is a little different than guideline or rule or what we've been talking about with some of the other keynote talks here, in that a goal is something that can be very difficult to achieve, right? So if you've seen my C++ seasoning talk, I have goals like no raw loops and no raw pointers. You can go watch the talk if you want to know what that means. Okay, but these are things that you strive for and that you don't want to put down as a hard rule. They're things that by striving to achieve them, your code will get better. So that's why I use the term goal. But what is an incidental data structure? Okay. To understand that, we need to understand what is a data structure. Now, most of us have a pretty decent idea. We're like, well, it's a list, it's a vector, it's a map. I looked up the definition. That's always a good thing to do if you want to know what something is. Definition is a data structure is a format for organizing and storing data. I'm not sure that I agree completely with the and storing data part, right? A data structure can be just a format for organizing data. You don't necessarily have to store the data inside the data structure. But that's not a bad definition. But in some ways, it's a little unsatisfactory because it really doesn't tell us what we mean by formatting and organizing. To understand that, we need to understand what is a structure. Okay? We can look up the definition of it, right? A structure is basically things that are related to other things. Okay? So how many people here have architect in their title? A few? Yeah? Software architect, some way, right? What an architect does is an architect designs structures, right? So what that means is an architect is concerned about the relationships in the software from one component to another. That's what an architect does. And there's a problem here. The problem is that computer scientists are very bad at relationships. We just are. Okay? So, this slide represents nothing, and I mean literally nothing. It's void. There is no dimension here. There is no width, there is no height, there is no time. This is a dimensionless space, if there could be such a thing, right? It is a mythical Haskell space, if you will. Okay? Within this space, we have 4 bits. Those bits have always been there. They will always be there. Okay? And those bits represent 4 bananas. That's what they mean. Or maybe they mean the color blue. Or maybe they just mean 4, an abstract 4. Okay? The reason why they mean that is because I said they mean that, because I think they mean that. Okay? That's a semantic relationship. Okay? Those bits have a relationship with the entity of 4. Okay? There's another relationship here. Okay? Those 4 bits collectively have a form, a type. They are related to a range -8 to 7. I bet a bunch of you thought they were unsigned, right? Yeah, but they're not. Why not? Because I said so. Okay, this is my universe. These relationships are incredibly important. Okay? When we heard talks earlier, and we were in Herb's keynote, he mentioned type safety, lifetime safety, bound safety. What we're talking about when we talk about those things is maintaining this relationship. Okay? If we lose the semantic relationship on our type, the universe unravels, missiles launch, it's really bad. Okay? We also have a notion of value safety, right? Which is whether or not those bits 0, 1, 0, 0 represent our 4, right? If we lose that relationship, right, then we have lost value safety. So when we lose that, we say our value became invalid. Now the standard, the C++ standard, actually uses the term valid in 2 different ways. Okay. In the first sense is talking about iterator validity. Okay. So if I have an iterator and it points into a vector and I do a pushback on my vector, the vector might move and my iterator becomes invalid. Okay, that's what the standard says. The bits in that iterator didn't change. What happened is the relationship that that iterator has with the vector was severed. Its meaning was lost. It's now an invalid object. The only thing that you can do with that invalid object, right, the type is not invalid, it's still an iterator, but its value is invalid. The only thing that you can do with that invalid iterator is either restore meaning to it by assigning a value into it or letting it go and destructing it. Okay. Now the other way that the standard uses the term valid is in talking about the state of an object after it's been moved from, or with the basic exception guarantee after an exception's been thrown. And there the standard says that the value within the object is valid but unspecified. That's a contradiction. Okay? If it's unspecified, it has lost its semantic relationship. It is no longer a valid value. Okay? Its type is still valid, but that's a given, just like an iterator type is still valid. Okay? So these are somewhat contradictory senses. So when we say with the basic exception guarantee or the state from a move from object, that object is now invalid, okay, because it's lost that semantic relationship. And the only thing meaningfully that we can do to it is we can establish a new value in its place with meaning, or we can let it go and destruct it. If you're familiar with the book Elements of Programming from Alex Stepanoff, he refers to an object in such a state as being partially formed. So these are very important relationships, right? So when we talk about safety in programming, what we mean by a safe operation is an operation that maintains the semantic relationship. An unsafe operation is an operation that may sever the semantic relationship. Okay? When we talk about invariants on a type, what we mean are the properties that must hold in order for this value to remain valid, to maintain its meaning. Okay? Everybody following that? Now we can have two objects within our universe here that have the same type and map into the same space. And that allows us to establish a value relationship. Okay? This is another type of relationship between those two things. 4 is less than 3. That's a mathematical structure, right? It's a value-based structure. We can also establish a relationship on just the representation, right? We just have these bits in memory. We can hash the bits, and we can talk about the bits being equal or not equal. The reason why hash has meaning is because of the relationship that if two objects have the same representation, then they represent the same value. Okay? So we are now associating a representational relationship, their hash, with a value relationship, and that's how we get meaning on hash. Okay, now the converse is not necessarily true. Just because the hashes are equal doesn't mean the values are equal. But we don't live in this mythical space. We live in this space. Right? We live within an address space. And what makes the 4, the 0, 1, 0, 0 in the middle there, different from those bits at the top is that those bits have no semantic meaning because I didn't give them any. Okay? So if I have an integer on the stack and it's uninitialized, right, that is an object in a partially formed state. It has no meaning. The only thing that I can do to it is assign a new value to it to give it meaning, right, or let it destruct. Now, my object within a space has a relationship with the space. It's the address of the object. And that's both spatial and temporal relationship, right? This object is here now. Okay, so where did John go? Is John in the audience here? John's back here, I think. Where's Marshall? Here. Marshall's back here. So John and Marshall are involved in a relationship. Okay? Normally, you would call this a structural relationship, but since we're defining structure, that's a bad term for this talk. So I'm going to call this a physical relationship. So John and Marshall are involved in a physical relationship. See, I'm getting back at John, right? And apologies to Marshall. Now, you guys laugh, but you're all involved in a physical relationship, which is a little scary, okay? That relationship has no meaning, okay? Okay, for some of you, maybe it does. Okay, these two items are involved in a physical relationship. The address of the first object is less than the address of the other object. That in and of itself has no meaning. Okay? But we can ascribe meaning to it by sorting our objects. And now what we've done is we've established a correlation between the values and between their physical location, and that lets us associate meaning with their physical location. Okay? This is an important property of having objects within an address space. This is something that we can exploit when we're building software, right? There's a lot of languages that would like to ignore the fact that objects have physical relationships, right? We refer to those as the Puritan languages, right? We all know the physical relationships exist, but they're being ignored. Now, there's another possible relationship here. If we take one of the mathematical relationships associated with our value and we associate it with a function, we get a functional relationship, okay? So here we can add our two numbers. We get 7 as our result. So that's a functional relationship. Functional relationships form dependency graphs. And if you want to know more about that, a little bit more anyways, look up my concurrency talk. I'm not going to talk too much about dependency graphs in this talk. But I will mention that if we were adding two values that overflowed, right? Remember these were signed values. My result is unspecified, right? What does that mean? It means that my value and my result has no semantic relationship. So this comes up over and over and over again. There's one more relationship that's of particular interest that I want to talk about. And this is the whole part relationship. This is defined in Chapter 12 of EOP. Okay? The whole part relationship is what allows us to talk about composite objects. A whole part relationship has 4 properties to it. The first property is connected. And what that means is that if I have an object that's a part of another object, that I can reach that part from the whole. Okay? So if you have an automobile, like a Honda Civic, and you have a part of your Honda, the part is connected to your Honda. The second is non-circular. And I don't mean in the sense that back pointers are disallowed. I mean that something cannot be a part of itself, either directly or indirectly. Okay? So no circular part relationships. The third is logically disjoint. Again, what I don't mean is that I can't have an object that is shared by two other objects, but what I mean by logically disjoint is that if I change one object, it cannot change the other object. Okay? So there's kind of no mutable sharing that can be allowed. So we don't have that. And the third relationship, the third property of this relationship is ownership. And what that means is that if I make a copy of the object, it makes a copy of all the parts, and I get 2 of them. And if I destruct one, it gets rid of that object and all of its parts. Okay? And those are 2 distinct disjoint objects. If you've ever heard the term regular types, these are the properties that allow a composite object to behave like a regular type. Okay. All the standard containers, vectors, lists, things like that are composite objects. So let's go back. What is a structure? Right? So a data structure is a structure utilizing value, physical, structural, and representational relationships to encode semantic relationships on a collection of objects. And the choice of encoding can make a dramatic difference in the performance of operations on these objects, right? And we know that, right? We know that if I have a linked list, that iterating over the link, that indexing into the linked list is linear time, and inserting into it is constant time. And if I have a vector, it's the reverse of that. Iterating over it, or indexing into it is constant time, inserting it into it is linear time, right? And we know that I can have a map where I can look up an n log n, and we know that I can have a closed hash map and get something close to constant time on a lookup. We know these things. Now, something that I think a lot of people don't realize is how big of an impact these days the memory hierarchy has on the performance of data structures. So I stole these numbers. They actually come from Jeff Dean, but I stole them out of a slide from Chandler. Jeff Dean also has a talk that's available online. So these are the times on a typical desktop machine to access different pieces of memory. There's basically an order of magnitude difference between each level in the memory hierarchy. Okay? So by the time you get down to main memory, it takes you 200 times as much time to get to something as it does out of L1 cache. That's huge. When I started programming, this was not the case. Not at all. It was much more one-to-one. On a modern machine, RAM behaves much like a disk drive. Okay? To put this in perspective, log of a trillion is 40. Okay? So an algorithm that's n log n versus an algorithm that's linear, okay, can be more impacted on its performance by locality of the objects than by the big O notation on the algorithm. Okay? So locality matters. Use arrays, use vectors. When I was researching this talk, I stumbled across an old post on Lambda the Ultimate that was citing the talk. The person who wrote this piece said it was either a talk that I had given or that Chris Cox, who's a member of the Photoshop team, had given. I don't recall saying it in a talk, so I'll attribute it to Chris. But that the Photoshop application, the #1 data structure used in the application, was vectors. And the person on Lambda the Ultimate concluded that Photoshop had no interesting relationships within the application. This is not the case. Okay? The case is that the team understands performance. So I want to give some examples here. The first example is utilizing parallel arrays with algorithms. Did I go? Okay. If you saw my C++ seasoning talk, there was I gave an example of an algorithm called gather, which comes from Marshall Clow, that uses two instances of stable partition in an interesting way. I gave that talk, and after that talk I went out to dinner, and I was chatting with somebody at dinner, I'm sorry, I don't recall who it was, who said, I really liked your talk, but you really cherry-picked that example. I think somebody here repeated kind of the gather and slide algorithms from that talk in one of their talks. And I said, I said, you know, it was a talk, so certainly I cherry-picked, but it wasn't that big of a stretch. And he said, well, algorithms in real life are very complicated. Okay? And I said, for example, he said, for example, you can't write stable partition simply. Yes, I can. Okay, so what's stable partition? Right? Stable partition is you take all the good guys, all the selected guys, you have some predicate that marks guys, and you move them all to the front. All the good guys go to the front. And all the bad guys go to the back. And it's stable because their relative order doesn't change. Okay, so that's stable partition. So we're going to write stable partition. Okay? Anybody know where to start? Wow. Standard library. We have stable partition, but we're going to write it for a reason. Okay? So what if we cut our space in half and somehow magically we were able to stable partition both of the halves? We still don't know how to write stable partition, but we're just going to assume that we could do that. Okay? By just calling stable partition 2 times. We still need to write stable partition, but this would work if we could do it. Okay. Now what do we have to do to get the good guys to the top and the bad guys down to the bottom? right? That range in the right order. Okay. Anybody know? There's an algorithm for this. Rotate. This is rotate, my favorite algorithm. So we rotate. Okay? Okay, so we can do that. And rotate is going to return the new midpoint. That's our partition point. So that's very handy. Okay? So we can just return that out of our function. So now all we need is an inductive basis. Where does this thing bottom out if we just recursing down? Just keep recursing down. Okay? We're going to recurse all the way down our tree. Well, we're going to end up with one element which is either selected or not selected. Okay? So we're going to apply our predicate to it, and we're going to return R there if it's selected. Okay? So we're going to move F down, or we're just going to return wherever F was, right? Right? So we're just going to add a 0 or 1 to our location, and that's our inductive basis. Okay? So now we can put a little boilerplate around it. We need to calculate how many elements we have. We need to handle the 0 case. And we need to divide to get our midpoint. And that's stable partition. We can execute that, and it will do that. Okay? People following that? Okay, so it's pretty simple. Okay? And in fact, if you look at all of the STL at the actual implementations, what you see is pretty much everything in STL is a building block to build one algorithm, which is stable sort. Okay. Okay. So rotate, if people aren't aware, the easiest way to implement rotate is 3 reverses. Okay. So you can write rotate. There's an interesting thing there, which is you can also write reverse in terms of rotate. And if you do, you can get an n log n version of reverse that works on forward iterators. That's left as an exercise to you guys. Now there's something very interesting here in this piece of code. The only place where our predicate is applied is one time to each object before that object's been moved. Okay? So we're going to go all the way down to the bottom of our tree, read each object exactly one time, and then put everything back together how we want it. Okay? That's an amazing property, and you probably wouldn't suspect that if you didn't know the implementation of stable partition. Okay? And what that means is that we can get an interesting algorithm out of this algorithm by just removing that star. Okay? So we can call this stable partition position. Right? What this allows us to do is our predicate can now be a projection based off the position. Okay? So let's call it. Let's see what I mean here, right? So I've got an array of integers at the top. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. And I've got a Boolean mask underneath that that happens to have a 1, a true bit, underneath every even value. Okay? Those are 2 parallel arrays. And what I want to do is organize A so that all the even guys, all the selected guys, are up front, maintaining the relative order, and all the odd guys are at the end, maintaining their order. And I can do that with the stable partition position. Okay, so that's what it will print, right? I stop in the middle there to put it out. So the result, what is in our A after we execute that, is 2, 4, 4, 2, 1, 3, 5, 5, 3, 1. Right? My predicate there is a projection from A, from a position in A, into a position in B. Okay? So if you saw my talk on what you can do with stable partition as far as gather within a UI, I can have a bunch of selected objects and I can move them into one location. Now I don't have to keep the data about where my selection is in the same data structure with the rest of my data. It doesn't have to pollute that and slow down my access times on that rest of the data when I don't need my selections. I can keep it as a parallel structure. It also means that I can take my selection vector here, my array of bits, and I could encode it in a more efficient manner, right? Maybe I could encode it as a set of inversion points to represent ranges that are selected, and I can project into that. Okay? So just changing that one character, just removing the star in stable partition gave me a new algorithm. So another example, algorithms and minimal work. Like stable partition, a lot of algorithms in STL work in a divide and conquer fashion, not just in STL. A lot of algorithms in general work in divide and conquer, right? There's kind of two ways that that can happen. You can, as we saw with stable partition, we can go all the way down to the bottom and then put everything back together on the way up. Or if you were doing something like a quick sort, you would pick a pivot element and you would partition at the top, and then you would go down the tree doing partitions until you got to the bottom, and then your whole thing would be sorted. Okay, so there's kind of two approaches that you can take. Both of these approaches lend themselves to pruning the tree, right? If you've got a tree structure, a lot of times you can figure out that you don't need to go all the way down to the bottom, and we can utilize that to get performance. So let's take a problem here. Okay, I've got this time a vector of numbers. Okay, the numbers I think here go from 1 to 16, and they're randomly shuffled in there. And I've got a range within that vector, SF to SL, that I want the values within that range sorted as if the entire vector were sorted. Okay? So what I want is 6, 7, 8, 9 in there, okay? But I don't actually care about anything outside of there. Okay, so I could sort the whole thing and that would give it to me. It just wouldn't be as fast as I would like it to be. Okay. Where do we start writing this? Anybody? Partition? Yeah. One vote. Let's see. I got Marshall back there in the back. He would be tempted to start with partial sort. Partial sort is part of the answer, right? I can't just use partial sort here because partial sort always works at the beginning of a range. What's that? Nth element. Thank you. Okay, so there is an algorithm in STL called nth element. So we can start with just the first guy in this, SF. And we can call nth element. And what that's going to do is it's going to do a form of a partial sort that just pins the element at our iterator SF with the right value, right? So after I do this, this is what my data is going to look like, right? The stuff above and below is still scrambled, but 6 is where I want 6 to be, right? So you want to calculate a median quickly with STL. Nth element is how you calculate a median quickly, okay? Okay, how many people knew that? Yay, know your algorithms. Okay, so from there now, it's pretty simple. If we know something a little more about nth element. Nth element doesn't just pin the one element, it also partitions our space. Specifically, everything between F and SF is going to be less than or equal to the value that's at SF. Okay? And everything down there is going to be greater. How many people knew that? Wow, a few. So about half as many people who knew what nth element was. So now, to complete things here, we already got that guy in the right position, so we can just skip over him. And then we can just call partial sort. Okay? So both nth element and partial sort are tree pruning algorithms. Okay? So that's going to get us those guys in the right range. Okay? So I can put a little boilerplate around here. I want to handle the empty case, right? I don't want to call nth element when there is no element there. And I can just skip the whole nth element thing if my range is already at the beginning. And now I've got a very beautiful little algorithm called sort subrange. If what I need is to sort a subrange, and I might do it because I'm doing something like taking an average around a median, or I might do it because I've got a view into a large collection of records and I just want to see this, or the user told me to print page 7 of 1,000 for my document, okay? There are many reasons why I want this data. In practice, this is going to be somewhere between about 2 and 8 times faster than sorting all the data, okay? Because we're cutting off the leaf nodes of the tree. Our sort subrange also inherits the same properties that we had in nth element, which is it also partitions the space. So everything from F to SF is less than SF, and everything from SL to L is greater than or equal to the last element within our range. And so if I need to extend it, right, down to NL, I can just call partial sort, and I can extend it. Okay? So what I'm utilizing here is I'm establishing spatial relationships on my object that capture semantic relationships about their value ordering, and I'm exploiting that to speed up my algorithm. Okay? So this is a data structure. This is structured data. Right? So what is an incidental data structure? Well, an incidental data structure is a data structure that occurs within a system where there is no object representing the structure as a whole. Or put another way, it's a structure formed in the absence of a whole-part relationship. It is not a composite object. So why don't we want them? They cause ambiguities in our code, right? Structural ambiguities, which is a little different than value ambiguities. They break our ability to locally reason about code. They break the notion of value semantics within our code. And they happen all the time. Okay? They happen when we create delegates. They happen when we have message handlers. And the biggest culprit is self-referential interfaces. Right? I remember when I was first learning C, and I discovered this amazing thing where I could forward declare a class or forward declare a struct, and then within my struct I could have a pointer to myself, and that's the basic concept with which I make a linked list. And I thought, oh, that's just amazing, right? Right? That even works. Okay. This API is also a self-referential API. This is pretty much the API for UI element out of the Windows API, right? Stripped down and C++ized, right? I got rid of kind of the managed C++ issues here. Okay. So what have I got? I've got elements. I've got an element collection to which I can add elements. I've got a panel, which is an element. Okay, and my panel has a bunch of children in an element collection, which are elements. And people tell me, well, what's the problem with this? It's a hierarchy, right? I mean, it works. Okay, I put an object in there. Is it a hierarchy? Right? What if I do that? If I put the element into the panel again? Okay, well, it's a DAG. We can deal with a DAG. The DAG's okay. Well, what if I do that? Okay, it's a DAG with 2 roots. or that. Okay? My API doesn't constrict those. Okay? You might think this is silly, but I've actually seen people do horrible things like this in code. Okay? With sometimes interesting results. Okay? What's going on here? We have managed, in those 4 lines of code, to violate every property of a composite type. Every single last one. Our panel is a part of itself, right? So it's circular. Okay? So it's not disjoint. We have 2 panels there sharing the same elements. Okay? So we violated ownership. If we destructed one, the whole thing did not go away. Okay. And potentially, we have a retain loop on our panel, and that would violate connectivity. Those 4 lines of code, we violate every principle for a composite object. So forests and hierarchies are so important because they appear in code all over the place, and they had to add a huge amount of complexity to the code. We've all gotten used to writing linked lists and vectors and things in terms of containers, and yet for some reason we persist in writing forests and hierarchies as intrusive data structures where we embed the information about the structure into the structure itself. And besides the structural ambiguities that I pointed out, this leads to all kind of algorithmic ambiguities. When I iterate over the children, okay, within my panel, am I just iterating over the children? Or is that a pre-ordered depth-first search? Or maybe it's a post-order depth-first operation, right? Because I don't know as I call each of those children what they're doing with their children, right? Right? And a lot of people tell me, well, this isn't too bad because hierarchies tend to be log n-ish. It actually is really bad. Hierarchies in real life tend more to be like n over 2-ish, right? Right? They don't fan out like that. If you look at view hierarchies, I have like a bunch of deep containers and then a bazillion children. Okay? I go like down and out. That tends to be more of the structure, right? Right? They tend to be a very inefficient way if I want to do something like very quickly determine where a mouse clicked within a view hierarchy. I don't want to go walk down my hierarchy and say, is it in you? Yes, okay, well check your children. Bonk, 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 all the way down. What I want is something like a quad tree, right, where I can very quickly navigate to exactly the object. I don't want the containment hierarchy. I want parallel data structures to keep that information. People tend to do event dispatching in these things where they keep throwing events back up to the top when really what they want to be doing is just calling another object directly a little over in the tree instead of percolating events up and down this hierarchy. Okay. And forests are somewhat difficult structures. Now, if I talk about a sequence, how many positions are there in a sequence? Okay. Anybody? If I have a sequence of n elements, how many positions in a sequence of n elements? N plus 1. There are n plus 1 positions, right? Right there. I can go between each of the guys in the element. Those are all the places where I could insert something. How many positions are there in a hierarchy? Anybody? What does it mean? Okay. First thing you have to define it. Is your hierarchy ordered or unordered? Right? That makes a difference. And what do you mean by position? It's a difficult thing. So a story here. Years ago, I'm sitting on the floor with my youngest son, and he's got a little fine motor skill toy, It's just wooden beads and shoelaces, right? And you string the beads on the shoelaces. How many people know what I'm talking about? Everybody, good. Okay. So you can do that. Put 2 beads on the shoelace. Now this is a pretty decent representation of a linked list, and that tells me how many positions are in the linked list. What would the corresponding structure be for a forest? Right? People are thinking probably a bunch of strings with a bunch of knots. Something messy. Okay. So I'm sitting on the floor with my son, and one of the shoelaces is tied into a loop. It's tied at the top. Okay? And the shoelace was fine enough that you could put the loop through a bead like that. You couldn't pass back through the bead because it completely filled the bead once you put the loop through the bead. So you could only put a loop through the bead once. Okay? So you could build a list this way. Okay. But any place where you could pull out a loop, you could put it through like that and create a forest or a hierarchy. I was very excited by this. Like, I spent 4 hours playing with this shoelace and beads. Anybody understand why I was so excited?
There's no knot.
No. Somebody. It is a sequence, okay? So it has lots of amazing properties. Okay? It is a physical model of a hierarchy, and the only thing that you can build with this is a hierarchy. Okay? The invariant that this thing stays as a hierarchy is part of the physical model of it. You cannot build a non-hierarchy this way. Okay? There is nothing that you can build with this physical model except for hierarchies. Okay? It also has some amazing properties in that, right, it's a little bit more complicated direction. Okay? So if we have the knot at the top, that's the piece that we hold on to, that's our forest. Okay? We can add a directionality to the string as far as how it loops around. Okay? Each position here represents a position where we could draw that out and insert another node. Right? We can't reparent things, but we can put leaf nodes anywhere. Okay? Just like on our original string, if we were just putting beads on to form a list, I can't move things further up without splicing, okay? But I can keep that ordering. In a similar way, I can always add leaf nodes to my tree, but I can't reparent things, okay? Every position within this list uniquely identifies a location within the tree without keeping a stack of information. I can have an iterator that points to a node, and I can just remember it and pick up from there and keep going in a traversal. Right? If I give you this definition that says we have a leading and trailing edge on our nodes, okay, then if I mark off the leading edge where I come in on the top, that is a pre-order depth-first traversal. And coming up from the bottom is a post-order depth-first traversal. Okay? If I want to know what it means to erase elements from some point in my model to some other point in my model, okay, what I do is I grab those 2 locations on the string, and I pick the whole thing up, and the beads that fall off are the ones that get erased. Okay? So above my fingers, going towards the knot, nothing can come off. Below my fingers, things might get stuck. If I grabbed along the same edge, I might end up with a list of parents that I didn't fully select. The string has to go through it twice for it to fall off between my 2 fingers. Okay? This means that if I take this structure and I flatten it out, and I encode it within a UI, it means that I know what it means if I click here and shift-click there and hit the delete button. Okay? And the algorithm in the code for this actually works out to be see what beads fall off, right? It's quite a beautiful little thing. Okay. So there's a forest data structure that's in ASL, that's been in ASL for years, Adobe Source Libraries, if you don't know what it is. It's decaying a bit, the source libraries are, but I keep this up to date on GitHub, so you can find the ASL repository on GitHub, and this will build, and this is what it looks like to insert things. And in my opinion, this is a really beautiful data structure. It's not a particularly efficient data structure. It's a node-based data structure, but that's what you would probably create anyways. But it has this wonderful safety attribute that I can't create a non-hierarchy. Okay? So it has these wonderful attributes that I can remember positions into it and deal with that. That when I iterate a range, I can see what it is exactly that I'm iterating. Okay? I'm not calling each node and saying, you call your children somehow. Okay? And I know if I want to do a pre-order or post-order, that becomes immediately apparent within the code. Okay. So 2 weeks ago, a little side story here. My wife was babysitting my younger son, whose beads I was playing with. He's now 26, right? So my wife was babysitting, and she keeps a box of old toys from when our kids were little. And she took it out since she was babysitting, and in that was a bag with the shoelaces and the beads, the actual shoelaces and the beads. And I had this very humorous thought that it's like, well, someday, maybe in a computer history museum next to Martin Newell's teapot, there will be Sean's shoelace. But I was surprisingly excited to see these. And I was like, I remember those beads. And I asked my wife, I said, do you mind if I take those to the conference that I'm going to give a talk at? And she said, why would you want to take them to the conference? So I tried to explain that, you know, the shoelace in this bead was a beautiful representation of a hierarchy, and that it maintained all these wonderful attributes. My wife's a nurse. And she wasn't looking at me like quizzically or with awe. She was looking at me with something that was closer to disgust. And she reached out and she took the beads back. And she said, that's what you remember? So computer scientists, we're bad at relationships. Okay, so conclusions. Understand the structure is created by relationships, okay, if you want to improve your code. Encapsulate structure invariants in composite types, and learn to use the tools that are already at your disposals and how to create new ones. Right? Last time I challenged you guys, those who were here 2 years ago, learn the STL algorithms, right? Now I mean really learn them, okay? So don't just read the interface and learn them. Learn how they're implemented, right? Learn how you would write your own. Okay? STL is intended to be an example. Okay? An example of how you code. So not a beginning, not an end. It's an example, right? So no incidental data structures, composite types, and better code. And that's it for my talk. I've got plenty of time for questions, if people have any. A question over here. You might want to come up to the mic if you can.
So you mentioned we can learn from the STL and the implementation of the STL. I'm also wondering, and I guess we could start with ASL also, could you point out some examples of C++ libraries today that best showcase the properties that you have talked about that we could also learn from by example?
Right. I mean, I certainly think you see them in Boost and in, the common libraries that you would think of looking. Unfortunately, STL itself, the typical sources that are on your machine, are so munched and so optimized that they can be very difficult to kind of plow through and learn from reading the implementation. A lot of times I'll go back to Alex's old SGI implementations, which are still online, to actually read the algorithms and what's going on there. The other thing to keep in mind when you're going through this, if you go through this exercise, is I think there's a lot of opportunities where we could improve on things. There's things like rotate has an implementation for how you do a forward rotate and a bidirectional rotate and a random axis rotate, depending on the concept satisfied by your iterators. Those are 3 different algorithms. And I don't know that anybody's ever gone back and revisited. I would almost guess that the forward iterator implementation for rotate beats the bidirectional iterator, which is running backwards on our disk drive of memory. And it might even beat the random access implementation, right? So kind of keep the history in mind there as you go back and look at the algorithms. The other great resource is Alex has course notes online, which are a little more approachable than something like EOP, right? EOP is a brilliant book.
So actually, I have also a follow-up question. Do you know anything like notes on programming by Alexander Stepanov? Do you perhaps plan to write something? Because I would be very interested.
Well, as I said, yeah, maybe I'll write a book. I keep telling people that people are like, where's the book? And I'm like, well, the only thing I have left to do at this point is write it. But that actually means I've done a lot of work, right? I've put together talks and notes, and I've taught the class, and so I have a big pile of material. But anybody who's written a book, I haven't, but I've worked with people who have. It's a lot of work. So yes, I would like to get a book out.
Thank you.
Question over here.
Hello. I would like to present a hypothesis to you and
Sure.
get your opinion on it. I think a common thread among your recent talks can be demonstrated if you consider code itself to be a data structure. Whether it's call graphs or a sequence of instructions or what have you. And when you think about a raw loop and all of the pieces that go into making a raw loop, you have iterators and increment operators, that can be seen as an incidental data structure.
Yes.
Do you see a relationship here between how we craft good code and how we craft good data structures?
I do. The term incidental data structure was actually coined by Jaakko Järve, who's a professor at Texas A&M. It occurs in a paper I co-authored with them on property models, which is about dependency graphs and flow of data within an application, and that creates a data structure. If you want to know more about that, as I mentioned, see one of my concurrency talks. Or you can look online. We've got a number of papers published on the topic. But yes, absolutely. In a more general sense, like I said, it's all about relationships and the structures formed in your code. And to understand a large system, you have to keep looking at how are the components connected. And they're connected in a lot of ways, right? There's different types of relationships. There's the functional relationships. There's the value relationships. There's the structural relationships. There's the representational relationships. And we exploit all of those, right? And then we have higher level relationships like whole part relationships. And we exploit that. So as you're looking at your code, ultimately what we want is the ability to reason about a piece of code locally. So if you look at every single chapter in here, what the punchline is how do I get my code in the point where I can sit down with one function and read that function and understand what in the world is going on with my code. Okay, so it's all about understanding these relationships so that you can reason about your code locally and know that as a whole, if it works locally, it's going to work at scale. So, yes, I agree.
So you've shown the importance of data locality for performance reasons.
Yes.
And as far as I understand, the forest implementation that you've shown was node-based. So
Yes.
how do you actually suggest to implement something like a hierarchical structure while having contiguous memory to benefit from cache locality?
So the question here was, my forest implementation is node-based. I mentioned that, and yet I already talked about the performance that you want by keeping locality. So could I recommend a structure for a forest that would keep locality? No, I haven't written one yet. I think somebody should. Maybe I should. I think it's doable. There's some hacks that you can do. I think our forest actually accepts allocators, so you can pull the same trick that you do that can have a serious performance impact on...
I saw a delete in there, so I don't know.
What's that?
I saw a delete keyword in there, so in the forest source code, a delete keyword, so I don't know if that's doable with the forest implementation.
Maybe not. Maybe not. I would have to go back and look. But you could retrofit it for an allocator if it doesn't already support one. I thought it did, but I could be wrong. Old memories. But yes, I think that you could build a structure that exploited the same properties but had better locality for operations.
Thank you.
Yep.
So one of the more well-established incidental data structures is that of iterators and the various containers that they iterate through. Have you given any thought to how we might sort of break that incidental data structure setup that permeates a lot of our code?
So I think most of the issues there come from misusing iterators. Right? I think you really want to keep your iterator usage encapsulated, right? The very fact that they can become invalidated means that they are in some sense unsafe and must be used with care. Unsafe doesn't mean bad. And recently I wrote a little blog post about Move that you can find online that I think has a beautiful little proof that says that there's a fundamental trade-off between safety and efficiency. And provably you cannot have both. Okay? So that doesn't mean necessarily that that's a horrible state of affairs. It just is the reality. Now there's a lot that we can do to improve safety. We've heard a lot about the libraries that Herb and Bjarne announced where we can improve safety without a cost of efficiency. And I think Eric Niebler is going to give a talk on Friday about the range library, and that gives us a higher level abstraction to deal with iterators to improve the safety around iterators. But positions exist, and an iterator is just a position into something. And positions are fragile, and it's unfortunate, but it's the reality. And sometimes you need them, right? It's very difficult to have something like a safe rotate operation where you don't just have a raw midpoint that's required to be within a range. Okay. So there's trade-offs there, right?
Thank you.
We can do better. Any other questions? Good, okay. So this was the very first time I've given this talk, so I apologize for running a little short. I actually thought I was going to run a little long, but I think I talked faster than I expected to. But if you have any feedback about it, approach me afterwards, because I'll probably repeat the talk at some point. So I'd like to get your actual feedback in. If you saw a typo on a slide or something, give that to me. But otherwise, we can break for lunch or later. So thanks, guys.